Hello students, I hope you're excited for today's lesson. Today's lesson is 6.4 out of the textbook, and we are going to be constructing confidence intervals for the variance, but most specifically the standard deviation of a data set. So far we have learned how to construct sample means when the standard deviation is already known. That's when we used a z-interval. But when we didn't know the standard deviation of the population, we used a t-interval. And in 6.3, we learned how to make confidence intervals for proportions. And that again was categorical data. So it's helpful to remember how this chapter in general is laid out. 6.1, 6.2, and 6.4 all deal with numerical data, where, if you're asking one member of the population, you're essentially recording a number. What is your IQ score? What was your SAT score? How long did it take you to get to school? What is your GPA? These are all numerical data. 6.3, we talked about confidence intervals for proportions, and that's when we dealt with categorical data. Do you like mayonnaise with your French fries? Yes or no? What color is your car? Okay. How do you take your coffee? With cream and sugar? Just cream? Just black? Okay, so confidence intervals for standard deviations and variances. So let's recall sigma squared is the variance and sigma is the standard deviation. Again, squared is the variance. Take the square root of the variance, you got yourself the standard deviation. And as I write here, again, we're going to be looking specifically at numerical variables as opposed to categorical variables. It's always question number one when you start a problem if nothing's given. If I'm asking one member of the population, is this a numerical variable or is it categorical? Okay, so what's the best way of estimating the variance or the standard deviation? Well, if you have your data available, use the sample standard deviation from your data. So the idea is if I have maybe a list of 10, say, SAT scores, I not only find the mean, x bar, but I also find S sub x, the standard deviation, and we had to do that for t-intervals. So it's not that far of a stretch beyond section 6.2. So the point estimate of the variance, sigma squared, is the sample variance, S sub x squared. Likewise, the point estimate of the population standard deviation sigma is the sample standard deviation S sub x. So the hard part, and today's lesson will strictly just focus on the chi-square distribution. The next video lesson I will actually put everything together where we'll build the confidence interval. But for this part of the lesson, we are strictly going to be looking at we're going to learn properties, we're going to learn properties of the standard deviation, of the chi-square distribution, and we are going to learn how to find critical values of the chi-square distribution, which I think is a little tough, but we know the basics already, so it shouldn't be terrible. So, heads up, I know it looks like it's chi squared. I know it looks like a big X, but this guy right here is the Greek letter chi. Looks like that. And it's chi squared. And yeah, again, it looks like it's pronounced chi, but it's actually pronounced chi. Chi. So I'm going to sketch out a couple chi-square distributions here, and like before, we're going to, our chi-square distribution is going to depend on the sample size. And as I start drawing these, you're going to see a couple properties already. Does that shape look symmetric? No, right? let's see where that peak is, where that highest point is. I'm making this up. It looks like it's about around 8. That's actually going to mean that this one right here, the red curve, is a chi-squared with 9 degrees freedom. And I'll show you the properties in just a minute, but I'm sketching out a few different curves. Sometimes we get really tall ones. Helps to make the sound effects. This peak looks like it's about 4. So this green one would be at 5 degrees freedom. And an interesting one is actually with 2 degrees freedom. Well, actually, one with 1 degrees freedom doesn't even really have a peak. It has a peak at 0, so this one in purple is 1 degrees freedom. And I'll do one more. Maybe something like this. This one's really long and drawn out. Has a peak right around 18. This is going to be with 19 degrees freedom. So hopefully we're noticing some trends, but let's go over the exact properties. Again, these are the properties. These types of things tend to work themselves into multiple choice questions on my tests, right? Was that a subtle hint? No, it was a direct hint. It wasn't very subtle, was it? Okay, property number 1. All chi-squared values are 0 or more. That is, they are never negative. You can essentially think, hey, if I take any number, even if it was a negative number, and if I square it, it becomes positive, right? Exactly the same idea. Because standard deviations, for instance, are always positive as they are, right? We never have a negative standard deviation. And again, the reason for that is when we calculate the standard deviation, I know it's been a while, but if you remember the actual standard formula for this, let's say the sample standard deviation was 1 over n minus 1, and then we needed to know the mean of the distribution. So that is, we took every particular value, added it, subtracted it from the mean, squared it, and then found the next value, subtracted it to the mean, squared it, added it to the next value. So the idea was that this number in here, after I squared it, that is, well, it's the square there that always makes it positive. So same idea, that the chi-squared values are always going to be positive themselves. I have skipped technically the definition of the chi-squared distribution because I just found that for the level of this class that more students were confused. So I'm just trying to get to the things that you really need to know without confusing you. Property number 2. Chi-square distributions depend on the degrees freedom. And just like a t-distribution, the degrees freedom is going to be a sample size minus 1. And we'll start having some problems where we'll both get a list of numbers and estimate the mean and standard deviation, and both times we'd use a t-interval for the mean, and the degrees freedom would be n minus 1, and we'd use a chi-squared distribution to find the standard deviation, and it's still going to have a degrees freedom of n minus 1, so they'll end up having the same degree freedom. Next property, and this is true of the z and t, and in fact any density curve, we already learned this one, but the area under the curve is 1. Got a switch slide, so hopefully you got everything you need, or if you're at home, you could just pause the video right here. So property number 4, still continuing here. Chi-squared, as you saw by my drawings, it's always skewed right. It is never symmetric. And the last property, this is a little different than the property that's in your book, but if you saw what I was doing when I sketched out the curves to begin with, I kind of said, okay, here's the peak, it's at 8, oh, that means it's 9 degrees freedom. Well, in fact, the mode or the peak of the chi-squared curve always occurs at one value less than the degrees freedom. That's on the x-axis. So I'm going to flip back to my screen of the curves that I just drew. Oops, just kidding, not that button. Excuse me. There we go. So again, if you look at, say, I'm going to pick on the gold one there. We had 19, it had a peak at 18 that actually meant it had 19 degrees freedom, or vice versa. If I knew it was 19 degrees freedom, then I could see this peak, even though I misdrew it a little bit, would occur at x equals 18. And just like here, for instance, you can take a look here at the green one, had 5 degrees freedom, but had a peak at 4. The red one had 9 degrees freedom and a peak of 8. And if you saw the one with 1 degree freedom, technically that has a peak at 0, which is why out of all of them, it's the one that looks kind of funny with 1 degree freedom. That would be a sample size of 2, but there's no, well, there is a peak, but it just starts at the peak and it works down. It almost looks more of a what we call an exponential function, like a negative exponential decay type function. Okay. So these are the properties of the chi-square distribution. Now the next part is, this is going to be probably one of the trickier parts of the lesson, and why essentially this is going to be the last part of this video lesson before putting everything together. But this is going to be finding the critical values of the chi-square distribution. So I actually just want to revisit, let's do an example. Find the critical value of z for a, I don't know, let's just make up a number, 72% confidence interval. Not that we ever use that. No, we use 72%. But when we did this for the first section, again, what we had was we were looking for the z distribution, and we remember a normal distribution, a z distribution was symmetric about 0, and it was perfectly symmetric. So when we had to find something like a 72%, the critical value at a 72% confidence level, we kind of said, okay, we needed the middle 72%, and then we needed to find the area under the tails, which we said was 1 minus c over 2, or 1 minus 0.72 divided by 2, which is, let's see, that's going to be what, 28? 28 divided by 2, so 0.14. That is, each one of these tails had 14% area. And then the way we kind of did this was we went to our z table, and if we just looked at the z values, excuse me, we were looking for the area to be 0.14, which I'm looking at my z table right now, trying to find the closest value. That's pretty good, 1.08. And technically I went in here and I looked at, like, okay, if I just found 0.014, this was negative 0.108, but I said always by symmetry that means that this other value is 1.08. Well, when we do this so this was our critical value of z, and again for a normal distribution, this is perfectly symmetric, so we just took the negative and the positive value, 1.08. Chi-squared, however, is going to be a little trickier. Chi-squared is going to be trickier because it's not symmetric. So if I needed to do this same thing, well, let's use a nicer confidence level. Let's say I'm looking for a critical value at 90% confidence level. Well, I still have the same idea that I need to find the middle 90%. But I'm going to have to, unfortunately, find 2 values as opposed to 1. Because this isn't symmetric, I can't just find one value and take plus or minus that number. So the idea here is that this is the middle 90%, and like before, the area under the tails is going to be 1 minus c over 2, or 1 minus, in this case, 90% over 2. That's going to end up being 0.05, and again, the idea is now that I have the middle 90%, that leaves 10% left over, and that 10% has to be evenly split into these two tails. So we're going to give these guys different names here. We're going to call this value on the left, of all weird things, the chi-squared value. Oops, sorry, that looks bad. Hey. We're going to call this one here chi-squared on the right, and this one chi-squared on the left. And that might break your intuition. You're like, hey, wait a minute, but if I look at this 90%, right, this is on the left, this is on the right, how come they're backwards? Well, really what we're saying is that this number is on the right side of 5% area. That is, it's like right of where the area on the right is, on the area on the left is 5%. And this one over here is going to be to the left of this 5% of area. And again, by symmetry, we can't just take this number and make it, you know, we're not going to find a negative number as it is. We said all these numbers are positive. So we're not going to find, we have to unfortunately find two different values. And we're going to use the chi-square tables to find these values. Let's try one. Let's say we are looking for this 90%. You should have the chi-square tables in front of you. And if you're in the classroom, these are on the back side of the t distribution, the t tables. And again, you can differentiate which side's which, because if you see on the t tables, it has a little picture of the bell curve or the t distribution, and you can see how it looks nice and symmetric. And on the back side is going to be the chi-square distribution, which is clearly skewed right. So let's find a couple. Let's just pick on 90%, and let's try for some different degrees freedom. Let's try one for the degree freedoms of 8, and then let's also find one for degrees freedom of 20. And again, we have to be a little careful. We're going to need two of them. We're going to need the one on the right and the one on the left. Okay, so let's go on our chi-square table. And okay, so step number one is going to be calculating this number that we already calculated, the 1 minus c over 2. We had to do that for the critical values of z as well. So for a 90% confidence level, that area is going to be 0.05. Now what we need to do is let's start out on our chi-square table, and if we look at that number 0.05, we line up the column with the degrees freedom. Okay, so actually right now is where I actually embarrass myself a little bit and tell you that you can't use the backside of the t tables for the area on the left. In fact, the ones on the back of the t table only give you the value to the right, so you can only find the chi-square to the left, not the ones to the right. But you can in the back of the book, and I will make these tables available for you on the tests and quizzes. In the table in the back of your book, it's table 6 in Appendix B. The way this table works, I'm going to choose a different color here, is it gives you all the area to the right of a particular value instead of to the left like we're used to. So let's start out with the easier one. The easier one is going to be figuring out the chi-squared value on the left. This is where we just look under the table and we line up our degrees freedom with this area on the right. So for 8 degrees freedom, since this is a 90% confidence interval, again, that leaves 10% left over. Evenly split into two tails will be 5% in each tail. So if I look at the, if I just line up 0.05 with 8 degrees freedom, I got 15.507. That's going to be my critical value on the right. Now what about this one on the left? Well, how much area is to the right of this guy right here for 95 for 90% confidence level. Well, it's not only that 90%, but now it's also this 5% too. So I actually, in this case, on this one I had to find the area to the left of 0.05. Here I got to use 95.95. Again, I'm on 8 degrees freedom. Line that up, and I got 2.733. See if you can do it for 20. Okay, so for 20 on the left side, again, and degrees 20, and still at a 90% confidence level. So I should have 5% to the right, and if I line up 20, I got 31.4. Sorry, where'd that go? 31.410. And how about on the left side? Good, I got 10.851, and again, I defined 95%. So let's do one more. I'll write this down in just a second, but if you're already ready to go, see if, let's change the confidence level here. Let's go crazy because it's Friday. Nope, just kidding. Let's try 99% confidence level. And let's try this for 6 degrees freedom. See if you could find the right and the left critical values. And for me, and I suggest this for you guys too, start out, draw the curve, figure out how much area goes into each tail, and again, I do this very intuitively because I just think of half of whatever is remaining, but if you want to use that formula, go nuts. Just keep working. So again, I think it's easier to get the chi-squared value on the left first. It's 6 degrees freedom. So we should just be looking under 0.005, and if you notice on your table, this is all the way on the right. 6 degrees freedom. I got 18.548. And again, I was lining up the 0.005. How about this one here? Again, what value do I need to look up? 99.5, and again, because yeah, this is the middle 99%, excuse me, and then I have to add that tail along with it because I'm including that to the right as well. So you actually find that this is going to be right in the first column at 6 degrees freedom, 0.676. Okay, I hope you found this lesson helpful. Again, it's recorded on video, so you can go back to it whenever you need to. Okay, thank you guys.